Well, welcome to particle physics. We're going to start off doing something a little bit different and beyond GCSE, just to see if you've got the right kind of skills that you need for doing this subject. We're going to try to find the charge on the electron. Okay, this will involve us doing some quite complex calculations, and hopefully we'll get some idea of the scale of subatomic particles. Okay, it's very difficult really. It's like the same kind of idea of astronomy, trying to get the idea of the scale of the universe. Is quite hard. Trying to go the other way and get the scale of some atomic particles is also very difficult, but at least you'll get some sort of handle on the sizes. So you should know from GCSE the unit for charge is the Coulomb, and you might think, I already know the charge on the electron, it's -1, but it's not -1 Coulomb. Okay, so what we need to know is what's the charge of the electron, not in relative units of -1, but in absolute units of the standard unit we use for charge in physics, which is the Coulomb. And if we know what the charge of one electron is, then we might be able to work out the number of electrons in 1 Coulomb of charge. So if you're talking in electricity about a current of 3 amps going down a wire, that's 3 coulombs of charge every second, you might get a handle on how many electrons that actually is that are moving down the wire. So it's quite a tricky experiment. Don't worry too much about the details of the experiment, just to give you a little bit of a flavour of the sort of skills that you're going to need. So what we're going to do is we're going to do some electrolysis of copper sulfate, and we're going to look at just the anode connected to the positive terminal. And what's happening at the anode is that the copper atoms that are in the metal are turning into copper ions in the water. Okay, in the solution here. Okay, these copper ions are going over to the other side, and they might end up depositing on this side, but we're not interested in that. We're just going to look at the anode. So think about what's going to happen. Here's our equation. The copper atom turns into a copper ion, and because copper ions are 2+, we get 2 electrons each time. Okay, the little animation will show you. There's the copper, it's gone into the solution, and the electrons have gone through, and we're going to measure those in an ammeter. So if you think about what's going to happen here, the anode is going to get lighter because the copper's going into the solution, and we can work out how many atoms have gone into solution if we're clever enough by working out how much lighter it gets. And the electrons are going to go through the ammeter, so we can work out the charge, okay, by working out the total amount of charge that's gone through the ammeter. Remember, the ammeter is measuring the current, okay, but if you might remember this equation, the charge is just the current times the time. So if I get 5 amps for 10 seconds, then I've got 5 times 10 is 50 coulombs of charge. Okay, so these are the two key ideas. We're working out how many atoms have gone in by weighing it, and we're working out how many electrons have gone through by measuring the charge and the time. Okay, so here's our little example calculation. This is an experiment where you had 0.2 amps flowing in the circuit for 20 minutes. The anode started at 3.45 grams, it ended up at 3.26 grams. Okay, so the anode's got lighter because the copper's dissolved. Every time an atom of copper turns into an ion, it releases 2 electrons. That's what's made this current. So the total charge that's flowed, the charge Q is the current I times the time. So here's the current, 0.2 amps. Here's the time, 20 minutes, but we've multiplied by the 60 to turn into seconds. So we've got 240 coulombs of charge. We can work out the mass of copper that's dissolved by doing the difference in the mass at the start and the mass at the end. So we've got 0.19 grams of copper that's dissolved. This is where it gets a bit tricky. You need to turn that into moles. So we need to know that 1 mole of copper is 63.5 grams. So we haven't got 63.5 grams, we've only got 0.19 grams. So we've got 0.003 moles of copper. Okay, you might hopefully have seen this number, Avogadro's number. This is the number of atoms in 1 mole. So we've got 0.003 moles times 6.02 times 10 to the 23 gives us 1.8 times 10 to the 21 atoms of copper that have dissolved. Okay, if you remember, we've got 2 electrons from each atom, so all we've got to do then is to double that number. So we've got 3.6 times 10 to the 21 electrons. So what we know now is that 3.6 times 10 to the 21 electrons carries a total charge of 240 coulombs. Okay, this is the crucial line. If some of that's lost you a little bit, don't worry too much. Just make sure you're clear that 3.6 times 10 to the 21 electrons, that's a lot of electrons, only carries 240 coulombs of charge. So to work out the charge that each electron's got, all we've got to do is to take the charge, divide it by the number of electrons that we've got. So we do Q, the charge, divided by, I've just used a big N there for the number of electrons, divide that, and we find that the charge on each electron in this experiment was 6.7 times 10 to the minus 20 coulombs. Okay, that's not the right answer. In fact, that's about half of the right answer, roughly. Okay, but that will give you an idea of how to do that calculation. Okay, so the crucial thing to realise here is this is a tiny number. This means that if we had 1 coulomb of charge, we'd have actually, with the correct number, about 6 million, 6 times 10 to the 18 electrons. And the point of understanding this really is to understand that the things that we're doing are very, very small, and a key thing to accept really all the way through this unit is that maybe the things that you're used to experiencing on the kind of scale that we live on, where you see whole amps flowing for minutes, is that if you've got things which are very, very small, they might not behave in the same ways that you're expecting them to behave from your experience, which is on a much, much bigger scale, where we're always dealing with millions and millions and millions of electrons at one time. So any random variations in what the odd electron might do won't be noticeable on our scale, but they might be quite surprising to you.